Organic Chemistry 1, Chapter 1 Basic Concepts in Chemical Bonding and Organic Molecules Practice Questions. Now, getting into this, it's important to note that Chapter 1 for Organic Chemistry is mostly just review of your previous chemistries and where it just sums up all the important information that you really need to know getting into organic chemistry. So, with that in mind, let's get into question number 1, which says determine the number of valence electrons for the following elements: boron, nitrogen, oxygen, chlorine, and magnesium. It's easy to determine valence electrons based on periodic table, where boron in group 13 has 3 valence electrons, nitrogen in group 15 has 5, oxygen in group 16 has 6, chlorine in group 17 has 7, and magnesium over here in group 2 has 2 valence electrons. So let's move on to question number 2. Identify the following bonds as polar or nonpolar. Now, if you remember, determine if a bond is a polar or nonpolar or not, the electronegativity difference has to be greater than 0.4. And electronegativity is how much atom wants to pull shared electrons towards itself. For example, fluorine over here has the highest electronegativity, so it wants to pull these shared electrons more than any of these other atoms. And a trend for if you don't have the electronegativities enabled is if you go to the right of the periodic table and up, the electronegativity will increase. So now let's look at the actual question. A carbon-carbon bond, they have the same electronegativity, so that's going to be a nonpolar bond. A carbon-hydrogen bond, where carbon is 2.5 and hydrogen is 2.1, so that's a 0.4 difference, so that's going to be a nonpolar bond. Now, boron-fluorine, where boron is 1.5 but fluorine is 4, that's going to be a 2.5 difference, so that's going to be a polar bond. And oxygen, those that are the same, so 0 electronegativity difference, so it's going to be a nonpolar bond. Carbon-nitrogen has nitrogen has a 0.3, so the difference is 0.5, so it's going to be a polar bond. And don't let that double bond trip you. It doesn't matter towards polarity. So, yeah, let's move on to question number 3, which says rank the following bonds in order of increasing bonding polarity. First, let's list out the atoms and their electronegativity. Carbon has 2.5. Sulfur has 2.5 right here. Oxygen has 3.5 and fluorine has 4. Now, carbon sulfur, they're the same, so it's going to be on the very left. Carbon oxygen has a difference of 1, and carbon fluorine has a difference of 1.5. So, in order of increasing, it's going to be carbon oxygen bond and then the carbon fluorine bond. Now, question number 4 says, draw the Lewis structure for the N2 molecule. Now, it's important to note the valence electrons for nitrogen. Nitrogen has 5, and since there's 2 of them, we're working with 10 valence electrons in total. So, let's first draw out the nitrogens. And if we were to draw a bond between these two nitrogens, each of these nitrogens contributed 1 of their valence electrons. 1, 2, for a total of 2, right? Each contribute 1, but since they're sharing these, each nitrogen has 2 electrons in their octet, right? So we add another one. Now each nitrogen has 4 electrons in their octet. Another one is going to have 6. Now, as I said earlier, we have 10 valence electrons to work with, and if we were to count 1, 2, 3, 4, 5, 6, they only use 6 of them. So we have to add 2 lone pairs over here, making it using up all 10 of our valence electrons. And each nitrogen has 8 electrons in its octet, so it's happy, right? Yeah, let's move on to question number 5. Why is the following structure not the best way to show the Lewis structure of CO2? Now, the big alarm should be the formal charges. These formal charges here, these are not needed. So we can just draw this Lewis structure without it. So we can draw this oxygen, And instead of one bond, it will have two bond to get rid of that formal charge. And instead, it will have two lone pairs, and this triple bond into a double bond. And yeah, and to tell that we did it right is we can count the valence electrons where carbon has four, oxygen has, um, if you look here, remember it has six. Sorry, I should do it here. And if you were to count all these valence electrons, it would go up to 16, which is a total number. But I'm not going to do that for the sake of time and move on to question number 6. Draw the new resonance structure and compare the relative stability. Show arrows in the original structure. Now, to draw a resonance structure, you have to draw the Lewis structure, but the connectivity has to stay the same. The only difference is the electron arrangement. For example, hydrogen is always going to have that sigma bond to that carbon, and this carbon is always going to have that sigma bond to this oxygen when drawing resonance structures, at least. So we all know that this is for sure correct. Now, the electron arrangement is going to differ. So these lone pairs and these double bonds, or these lone pairs, something is going to change here. And what's going to change is this double bond here is going to move and form a lone pair on that oxygen. And this lone pair is going to form a double bond on this, form a double bond for the carbon oxygen bond. So when drawing it, we're going to have three lone pairs here with a negative charge here, and a double bond here, and it's going to be a positive charge. Now it shows which is more stable, and this one's more stable because it doesn't have these formal charges, these unneeded formal charges, so it's going to be more stable. So let's move on to part 2. As we're saying, we know that this is going to be correct in the resonance structure. Now, this lone pair is going to form a double bond and have a triple bond on that nitrogen. But if you were to notice, if we were to draw this triple bond, you should be very alarmed by this, because this nitrogen here has 5 bonds around it, and that would violate the octet rule. So what happens is this double bond here is simultaneously at the same time is going to form a lone pair on that carbon. So this nitrogen would never have 5 bonds attached to it. And what that looks like is this carbon will have its lone pair, and will have that negative charge, right? Because it has 5. It quote unquote owns 5, right? 4, 5. So that's one more than its valence electrons in the periodic table, which is 4. So it's gonna have that negative charge, and this nitrogen is gonna have that positive charge. And I forgot to draw the triple bond, but there's gonna be a triple bond there. Now, when it comes to stability, the only difference between these two resonance structures is that this carbon has the negative charge, while in this one, this nitrogen has a negative charge. And this one is going to be more stable because since nitrogen is more electronegative, it's going to be able to hold on to that negative charge better than a carbon, which is less electronegative would. So, question number 7. What is the hybridization of the xenon atom in xenon fluorine 4? And what is the shape of the whole molecule? Now, let's first draw xenon F4. So we know that xenon over here has 8 valence electrons, and fluorine has 7 valence electrons. And as I was saying earlier, fluorine really wants that shared electron, so it's going to have that one bond with xenon. So we know that this is correct. All right, he's going to have those 4 bonds around it. That's in hydrogen, sorry. He's going to have those 4 bonds around it. And don't forget the lone pairs. Now, each of these fluorines are happy, right? Because there's eight electrons in each octet, and yeah, it fulfills it, and it's happy. But the thing about octet is that um, if you're third row and down, they can actually have a thing called expanded octet, which xenon is, right? So the xenon, while the octet rule says you can only have eight, xenon actually has expanded octet, so it can have more, right? Because xenon has the eight valence electrons, but only in here it only has the four, right? So we have to draw those two other lone pairs, making it eight. Um, and just if you want to make sure, you can always count the number of valence electrons on this molecule, and find the number of valence electrons on the periodic table. Like for example, it'll be 7 times 4 because it's 4 fluorine plus 8, which equals 36. So if you count all these valence electrons here, all these electrons here, there should be 38. And if there is 38, that's how you know you did it right. But this question is talking about hybridization. And the what I like to do for hybridization is first count the number of groups there are. So groups are lone pairs or bonds, right? Double bonds, double bonds, single bonds, or triple bonds. They don't matter. Those are all count as one group, right? So if you look at this, for example, I already counted 1, 2, 3, 4, 5, 6. There's 6 groups here. So the hybridization number for a 6 group a molecule, I like to find it by going increasing in order. And what I mean by that is a 2 group molecule would be sp. A 3 group molecule would be sp2. A 4 group molecule would be sp3, and a 5 group molecule would be sdp3, and a 6 group molecule, which is a xenon F4, is going to be sd squared p3. And so yeah, that is the final hybridization. I'm just going to write that over here. Whoops. So this is the final hybridization. Wait, sorry. This is supposed to be a D, not a P. D2 and then S. Now, if you notice that it just increases by 1. So that's how I like to think of it. Just count the group numbers and simple from there. And it also says what is the shape. And for the shape, we have this handy dandy chart right here. These Vespers geometries. Now, you would have to memorize these, but for sake of video, I have this chart here. So we know steric number is just the amount of groups it has, and as we said, it has 6 groups. So it's going to be a 6 steric numbers. And the amount of lone pairs it has 1, 2. So it's going to have 2 lone pairs. So it's going to be a square planar shape. And yeah, that's how I answer this question. And that was all. And thank you for watching.